Welcome everyone. I'm Norman Wildberger. In this video we're going to look at some basic laws of arithmetic, the commutative laws for addition and multiplication, and we're going to investigate them from the point of view of geometry. So it turns out that geometry is a great way of thinking about why these laws actually work. So along the way we're going to introduce some nice transformations of the plane, very simple ones that are going to be very useful for us in the future too. So we're interested in just basic arithmetic, addition and multiplication with a very simple-minded framework, the kindergarten framework to arithmetic that we've been talking about, where a number is just a row rectangle. So here, for example, is 2 plus 5. There's the number 2, there's the number 5. When we add them, it means we put them together. So there's the join right there. And then we count how many cells are in the total. 1, 2, 3, 4, 5, 6, 7, because we now have names for the first 10 or so numbers. On the other hand, 5 plus 2 is what we get when we start with 5 and then add a 2. We put them together in the same way. Now the separation is right there. And lo and behold, when we count, we get 1, 2, 3, 4, 5, 6, 7. Surprise, surprise, we get the same thing that we did when we added 2 plus 5. So we conclude that 2 plus 5 equals 5 plus 2. That is an example of the commutative law for addition. There's also a commutative law for multiplication, which is a little bit more subtle. So here's 2 times 3. We're thinking geometrically. 2 times 3 by definition is the number of cells in a rectangle whose dimensions are 2 and 3. And we can think of this rectangle as consisting of 2 rows. That row there with 3 elements, and that row there with 3 elements. And when we're adding up the whole cells, we're really just taking the sum of the 2 numbers in the 2 rows. That's formed by combining them in the usual way, and then we count that the total is 6. If we multiply in the other order, 3 times 2, then we're talking about a rectangle whose shape is different, which now has 3 rows and 2 columns. And now there are 3 rows each with 2 entries. So we're really adding 2 plus 2 plus 2. 2 plus 2 plus 2, when we put them together, they form a string like this, and lo and behold, we still get 6, the same that we got previously. So we conclude that 2 times 3 is 3 times 2. That's the commutative law for multiplication, that's the commutative law for addition, and it doesn't matter what the actual particular numbers are that we're using. If we had used 4 times 5, we would have gotten equals 5 times 4. If we would have added 3 plus 8, it would be the same as 8 plus 3. So these are general laws that apply no matter what the 2 numbers involved are. And today what we want to do is we want to think about why these laws are true by explaining them in a geometrical context. In particular, we want to introduce 2 very nice operations or transformations of the plane, the translations and the reflections. So let's introduce translations of the grid plane. So here's our grid plane, or at least part of it. And let me just remind you of a few basic notions. So the grid plane is composed of horizontal lines, which we call grid lines. They're equally spaced. And then there are also equally spaced vertical lines, forming this pattern of little unit squares or cells. The places where the lines meet are called points or grid points. And if we have a little 2 grid points on a line, then the part of the line in between those 2 points is called a segment. So for example, that's a segment, that's a segment. And we can also construct things like rectangles with 4 corners created by 4 lines, 2 in each of the directions. So now we want to talk about movement. When we're talking about objects, we're talking about nouns, we're talking about things. We want to also, in mathematics, move things around. So we want some kind of verb-like ideas. And the simplest kind of movement of the plane is a translation. And there are 4 sort of simplest translations corresponding to the 4 directions that we can go in. Now in terms of directions, we have sort of 2 choices or 2 systems that we can work in. We can think about the directions as being left and right in the horizontal directions, and up and down in the vertical directions. Or we can adopt a point of view of like a map. Think of this as a map with an east-west orientation in the horizontal direction and north-south orientation in the vertical direction. So there are kind of 2 systems here that are pretty complementary. Let's stick with this system today. So we're going to talk about moving left, or moving right, or moving up, or moving down. And corresponding to those 4 different directions, there are 4 basic types of movements. Translation T sub r, which is a movement of 1 to the right. So for example, if we started with this point A, and we applied TR, it means we're going to move 1 to the right. So it means that we would go from here to this point B. If we applied T sub r again, it means we would go from here, this point B, to this point C. And we could keep doing that. We could keep applying a translation T sub r, and we would be moving 1 step to the right at each time. T sub u represents a movement of 1 up. So from here to here, from C to D, that's T sub u. Or from D to E, that's also T sub u. Of course, there's also the other directions. So we don't just move right, we might want to move left. So T sub L is a movement of 1 to the left, and T sub D is a movement of 1 down. So these 4 basic operations, we can think of them as applying not just to the points, but actually to all the objects that we can think about in the grid plane. For example, to grid lines, to segments, to rectangles, and to other kinds of objects in the grid plane, some of which we'll be talking about today. So for example, let's have a look at this segment S. If we apply the translation T sub r to it, there it is right there, then both of the endpoints will move over to the right, and so the whole segment will move over to the right, and so that'll mean that S goes to R. On the other hand, if we had applied T sub u to S, then that segment there would go to that segment there, which we're calling Q. So we can move segments around using our basic translations, left, right, up, and down. We can also move cells around. For example, that cell there called X. If we move it 1 to the right, we get Y. If we move Y 1 up, we get U. Conversely, if we start with U and we go down, we get Y, and if we go left from Y, we get X. Now these things can also be combined to get what we might call composite translations. So where we're not just thinking about just taking 1 step in one of the basic 4 directions, but we're thinking about a larger step which consists of a certain number in the horizontal direction and a certain number in the vertical direction. So consider, for example, the relationship between this rectangle Z and this rectangle W. They're both the same shape. They're both 2 by 1 rectangles. So we might say that they're identical rectangles, but they're in different positions. If we want to move from this one to this one, how could we do that? Well, we could think about moving the entire rectangle 1 to the right, and then 1, 2, 3, 4, 5 up. So that composite translation, 1 right, 5 up, would get us from Z to W. However, there's no translation that's going to take Z to this rectangle V, because this rectangle V is not identical to it. It has a different shape. This is a 1 by 2 rectangle. So a translation, even if we move it in this area up here, it will not coincide with V because we're not allowed to twist or rotate when we're translating. That's a different kind of motion. Of course, we can apply it to more complicated things too. So if here is some kind of rectangle in the plane, then we can translate that in various ways. For example, that would be a translation of 2 to the right, and then 3 up would be here, and then maybe 4 left would be here, and then down 1 would be here. Right? So we can perform various translations of objects within the grid plane. And we're going to stick to translations where we're always going a certain number of units to the left or right, a certain number of units up or down. We're not at this point going to consider a translation where we go kind of halfway. Later on we'll think about that kind of thing. Right now we're always sticking within this framework of the grid plane. So those are translations. Another very important type of motion in the grid plane is a reflection. Reflections, just as the name suggests, are something like what you see in a mirror. When you look in the mirror, you're seeing a reflection of yourself. It's like there's another copy of you on the other side of the mirror. So what we need for a reflection is a line. And we're going to talk first about grid lines. There, for example, is a grid line. It's one of the lines in our grid. Let's call it L. And associated to that, we're going to define the reflection R sub L, the reflection in that line L. So what does that do? Well, just like a mirror, it takes points on one side of the line to points on the other side. So that point A there, when we reflect it in this line L, we would get this point A prime. And conversely, if we reflect A prime, we get this point A. So these 2 points are interchanged. What about the point B? Well, to see where it goes, we would have to go along a horizontal line perpendicular to the axis of reflection. And if we go 2 spaces to the line, that means we have to go another 2 spaces to get to the reflected point. So there's B, there's this reflection B prime. This point right here, C, is actually on the line. And when we reflect it, well, it doesn't change. It stays where it is. But we're free to not just reflect points, we can also reflect segments. For example, this segment, say here, the segment S, if we reflect that, we get this segment here. Just a segment between the reflections of the 2 endpoints of S. Or we could reflect, say, a rectangle. Here's a little rectangle X. If we reflect it in L, we get the rectangle X prime. This rectangle right here has the property that when you reflect it, it stays where it is. It doesn't change. The corners will reverse, but the actual rectangle itself, the total rectangle, stays where it is. Now, I'm going to now introduce a slightly more fancy kind of object. After all, points, lines, segments, rectangles, a little bit boring after a while. We'd like to have some more interesting figures. And let's introduce this kind of object right here. Okay? It's called a polyomino, like domino except poly. And it's a figure that we're going to talk about quite a bit later on. So this is just one example of a polyomino. It's a very simple example made out of 3 cells. The cells are connected along edges. So there's one called L, and there's another one called L prime, and I hope you can see that the reflection of L is L prime. Now you can see that by just going one point at a time. That corner there has to go to there, that corner there has to go there, so that line there has to go there, and similarly you can follow around what happens to the whole boundary. It gets mapped to that one there. So reflection in L interchanges this polyomino with this polyomino. So, well, we've talked about reflections in this vertical line L, but it's also possible to talk about reflections in a horizontal line, and that will be much the same story. For example, that point there will be reflected to that point there. This polyomino there will be reflected to another one down here, which will be in those 3 blocks there. But in fact, there are other possibilities for reflections too, and some of those are also going to be interesting for us. All right, so remember that we usually get some exercises to do, and here are some exercises that let you play a little bit around with this idea of reflection in lines, which is actually a very interesting idea, and it's a lot of fun playing around with reflections, in fact. So we're working in this grid plane here, and we have a few special lines defined. So this line here is the line L, this line here is the line M, and this vertical line is the line N. And then we have a few objects around. There's an ordinary rectangle, let's call it D, because it's a domino. And then we have a bunch of polyominoes. There's one called L, for obvious reason. There's one called T, and here's another one called Z. All these 3 have 4 cells in them. Now the first exercise is to ask what happens to one of these if we perform 2 reflections. First one reflection and then another reflection. So draw pictures to show what happens at each stage. Say in the first case, if we start with this rectangle D, and then we apply reflection in L, and then we apply reflection in M. So this is meant to be read from left to right, just like you ordinarily read. That's what we're starting with, and then we apply this transformation, and then we apply this transformation, and we get a new object, and we want to know where is that new object. So to do this exercise, or these exercises, I want you to actually work with a piece of graph paper in your book and make diagrams, copy this down faithfully, and then see what happens. You can do separate ones for the 4 different shapes. So for example, just to give you an idea, the first one, if you start with this rectangle D here and we reflect in L, well, you're going to get something that's down here somewhere. And then after that, if we reflect in M, well, we're going to get something which is up there somewhere. So the net effect is to go from here to there. So the idea is to see what happens to T, to L, and to Z when you apply that particular combination, reflection in L and reflection in M. And after you've done that, then you should get a sense for what this combination does in general. You can think about, if we applied it not just to these 4 but to some other shapes, what does reflection in L followed by reflection in M do more generally? The other exercises are very similar, except we're just using different lines. So exercise 5.2, exactly the same, except the combination we're interested in now is not this one followed by this one, but rather this one followed by this one. A horizontal reflection followed by a vertical one. And then same for R sub M followed by R sub L, and same for R sub N followed by R sub M. And this one here, a little bit fancier, what happens if you perform all 3 reflections in this particular order, L, N, and M. You might like to think, what happens if you change the order of the reflections? Does that make a difference? What kind of a difference does it make? So it turns out that the arithmetic of reflections, so to speak, is actually quite an interesting arithmetic. And we'll talk about that a little bit more, but right now just have some fun drawing diagrams and reflecting things, getting used to seeing what reflections do. Up till now, all the points and lines that we've been considering are actually grid points and grid lines. But pretty soon we're going to want to be a little bit more general and consider other points too and other lines. And we're going to now consider what happens if we reflect in a non-grid line. And there's going to be two examples that I want to tell you about. One is an example like this, where the line L is definitely not one of the standard grid lines. It's actually sort of halfway between this grid line and this grid line. Okay, we still sort of draw a line sort of halfway between them and ask, does it make sense to reflect in that line? Well, actually it does. Because a point like this, for example, will be reflected to a point on the other side of the reflecting line, an equal amount on the other side. So that point will go to that point. Or say that point there, 1, 2, 3.5, half, 1, 2, 3. So this point will be reflected to this one, and vice versa. Then you can check, for example, that this rectangle is reflected to this one, and that this polyomino is reflected to this one. It's a lot like the reflection in a grid line, except it's a little bit different because there's no actual grid line or grid points which are fixed, which stay where they are. So once you have that idea under your belt, now we're going to consider a little bit more subtle kind of reflection, where we're going to introduce a different kind of line, a diagonal line. So what does that mean? Well, we'll start with any point on the grid plane, any grid point. And let's consider another grid point, which is 1 over to the right and 1 up. So we translate to the right by 1, and we translate up by 1. Go from here to here. And then we repeat that. And again, and again, and again. Then all those points there lie on a new kind of line, which we'll call a diagonal line. And its name happens to be M in this case. We could also have gone in the other direction, so starting with this point and gone left and up, left and up. That would make that line there, which is called N. So let's talk about reflection in this diagonal line M. What does it mean? Does it make sense? Well, actually it does make sense. So let's have a look. So this point here, for example, its reflection had better be this one here. This point goes to that one. We're moving sort of perpendicularly to the reflecting line and an equal amount on the other side, and lo and behold we end up on another grid point. That's the important thing. So we go from one grid point to another grid point. This point here, its reflection, well, we're going in this direction, so one sort of diagonal step and then another diagonal step ends up on another grid point. So these 2 points are interchanged. In fact, you can see that this rectangle here, for example, is reflected to this one. This polyomino with 4 cells is reflected to this polyomino with 4 cells. Please check that. So for example, the reflection of this one is this one. The reflection of this point is this point, and so on. Now this kind of reflection does something that the other reflections didn't. It actually changes the shape of the object. For example, this rectangle, which was a 2 by 1 rectangle, has now been changed to a 1 by 2 rectangle. So the orientation has been changed. Okay, so and here's a little exercise for you to think about a case where L is some diagonal line, like one of those, either in that direction or that direction, doesn't matter. And M is some horizontal line, doesn't matter where it is. And then describe the effects of r sub L followed by r sub m, and r sub m followed by r sub L. So actually draw some diagrams, like you might say, okay, we'll let that be L and that be M, and then we'll draw some various shapes, see what happens when you reflect in L and then reflect in M, or the other way around. Okay, so I want you to put pen to paper, draw some pictures. You don't have to be at all artistically inclined because everything is taking place in this grid plane. All what you ever need to do is join points on the grid plane with lines using your ruler. So no artistic ability required. So now let's return to our two operations in arithmetic, addition, multiplication, and these two important laws, the commutative law for addition and the commutative law for multiplication. So the simplest one is the commutative law for addition, which says that for any numbers m and n, m plus n is the same as n plus m. In other words, it doesn't matter what order you add two numbers, the answer you get is independent of which order you add them. So for example, 2 plus 5 is 5 plus 2, or 3 plus 4 is 4 plus 3, or 7 plus 8 is 8 plus 7, or 168 plus 497, or 497, is the same as 497 plus 168. We may not even be able to add those things up, but we know that whatever those two things add up to, it's going to be the same as what these two add up to. Okay, so let's have a look at this example, 2 plus 5. Why is 2 plus 5 the same as 5 plus 2? Well, here again is 2 plus 5. Put it together, get a string there with the 2 there, the 5 there, separated by a little line. Let's call that line L. And now we're going to think about reflecting in this line L. This is all just in a row, but we can kind of imagine that it's all taking place in some larger grid plane. We just happen to be looking at a particular segment of it. So here's a line L. Okay? And what happens if we reflect this row rectangle in L? Well, it just gets flipped over. There's the result of that flipping over. So there's the line where we've reflected. So the 2 that were on this side, and now 2 on this side, the 5 on this side get moved into 5 on this side. And we see now that that's really the same as 5 plus 2. So this operation of interchanging the two numbers that we're adding corresponds geometrically to reflecting in a line, reflecting the row rectangle corresponding to the number in a certain line. And it's the fact that that reflection doesn't change the number of cells that allows us to conclude that the number of cells here is going to be the same as the number of cells here. So that 2 plus 5 is the same as 5 plus 2. Now this argument is general, meaning that it doesn't really matter that I'm using 2 and 5. If I'd been using 3 and 4, or 7 and 8, or 168 and 497, the argument is still essentially the same. Still essentially the fact that reflection in a line doesn't change the number of cells in that rectangle. It's not a very difficult result. Perhaps you think it's kind of obvious anyway. But it's still nice to have a kind of a reason, an explanation for why addition is commutative. It's a very important fact, a very useful, important fact that we use all the time in mathematics. The fact that we can change the order of two numbers when we're adding them. Just to skip ahead a little bit, notice that it's not true if we replace addition with subtraction. For example, 4 minus 1 is not the same as 1 minus 4. Or division. 4 divided by 2 is not the same as 2 divided by 4. So commutativity depends on the operation. Some operations are commutative, some are not. And here's a sort of a geometrical explanation for the commutative law for addition. Now let's have a look at the multiplication story, just a little bit more subtle. So the commutative law for multiplication. It says that for any numbers m and n, m times n equals n times m. So for example, 3 times 4 is the same as 4 times 3. This is probably one of the first examples of a non-obvious result. So if you think this is completely obvious, then you probably have not understood multiplication. Okay, this is not completely obvious. Let's explain why. So what is it we do when we multiply 3 times 4? 3 times 4. Well, in terms of our kindergarten numbers, there's 3, there's 4. What do we do? What's the definition of 3 times 4? The definition is we're going to create a rectangle. The rectangle has 3 rows and 4 columns. It's a 3 by 4 rectangle. The 3 comes from the first number. The 4 comes from the second number. And then we're going to think about adding up all the cells in this rectangle. And we can think about rows of this rectangle because each row is itself what we're calling a number. That first row is the number 4. The second row is a number 4. The third row is a number 4. So what 3 times 4 effectively means, it's 4 plus 4 plus 4. It's 3 lots of 4, or 3 groups of 4, or 3 copies of 4 added together. Okay, when we add those together, 4, 4, 4, we get that big number there. And how do we count that? Well, we peel off 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We'll make a little marker. That number there is the same as a single 10. Then we have 2 left over. So the answer in Hindu Arabic form is 1, 2. 1 10 plus 2 1s. Okay, we have the name 12 for that, but that's a little bit arbitrary. It's the Hindu number 1, 2. 1 10 plus 2 1s, or 10 plus 2. That's what 3 times 4 is. So it's essentially 3 groups of 4. What is 4 times 3? Well, it's the same kind of story. Now we have 4 here times 3. We have to make a rectangle which has 4 rows, the first number, 3 columns, the second number. It's a different shape from the rectangle that we had there. We think about its rows. Now there are 4 rows with 3 each. Here we had 3 rows with 4 each. Here we have 4 rows with 3 each. So that's another way of thinking about what 4 times 3 means. It means 4 groups of 3, or 4 lots of 3. 3 plus 3 plus 3 plus 3. When we put those all together, there's 3, there's another 3, there's another 3, there's another 3. Then we count this, peel off 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That group of 10 is a single 10. 2 left over, we get 12 again. So 3 times 4 is 4 times 3. We've computed both sides and we've seen that this is the case. Now, it's a little bit of a subtle thing here, so let me make sure that you appreciate this a little bit. Suppose you were a one-dimensional creature and you just sort of lived in a linear line. So you could imagine that number in your world, that number in your world, that number in your world. So 3 4s, 4 plus 4 plus 4. You can imagine them stacked together. And then in another situation you have 4 3s, 3, 3, 3, 3. So the question is, why should it be that 3 4s is the same as 4 3s. In other words, if you just looked at this number and you looked at this number, it's not at all so clear, unless you're very mathematically gifted, it's not at all so clear why this total should be equal to this total. And if the numbers were a little bit bigger, if I was multiplying 8 times 9, well, that would be 8 groups of 9, and that would be 9 groups of 8. Why are those the same? The point is that just in a one-dimensional situation, it's hard to see what's going on. But it's actually exactly for this reason that we introduce this two-dimensional aspect to multiplication. Multiplication is not just stringing these things together. It's actually making this rectangle. At the level of rectangles, there is a very reasonably simple reason why the number of cells in this rectangle is the same as the number of cells in this rectangle. As two-dimensional creatures, or actually as three-dimensional creatures which are very good at visualizing two-dimensional things, we can easily see the reason why this rectangle has the same number of cells as this one. The reason is, to get from one of these to the other, we just flip it over. We just reflect in a diagonal line. So it's also a reflection, but it's a reflection in a diagonal line. Let's see how that goes. So the commutativity of multiplication boils down to another geometrical observation, that the number of cells in this 3 by 4 rectangle is the same as the number of cells in this 4 by 3 rectangle. These rectangles have the same size. And the reason, we can reflect in a diagonal line. So imagine this is part of the grid plane, and I've just identified part of it, and there is that first rectangle that we're looking at, the 3 by 4 rectangle. There it is right there. And we choose a diagonal line. In fact, it doesn't matter which diagonal line we use. Let's use this diagonal line. Okay, going through this point, this one, this one, this one, this one. What happens when we reflect the rectangle in this line? Well, this point stays where it is. What happens to this one? It goes there. What happens to this one? It goes there. We're getting exactly this picture here. So this point here goes to that one. This one goes to that one. And this point here, it goes to there, which is there. So the 4 sides go to these 4 sides. The 3 by 4 rectangle goes to the 4 by 3 rectangle. It's just a flip in a diagonal line. We are very sophisticated visual creatures. For us, visualizing this flip is pretty simple, because we have a lot of brain processing power that allows us to manipulate two-dimensional images like this. If you were a one-dimensional creature, this argument would be very fantastical and hard to imagine. You'd probably have to proceed in some other more indirect way. So this is a visual argument that's accessible to us because of our rich visual nature. The fact that we can understand the geometrical aspect to this algebraic result. And some other examples. Of course, it doesn't matter what the two numbers are. The same argument's going to work. 2 times 5 is the same as 5 times 2. And what that means, another way of saying it, is that 2 groups of 5 gives you the same as 5 groups of 2. Or 3 times 13 is 13 times 3. Or 456 times 3 is the same as 3 times 456, etc., etc. The one law has many, many different particular instances of it. There are other important arithmetical laws that we're going to get to later on. Okay, there's also something called the associative law and something called the distributive law, and they're going to play an important role in arithmetic too. But it's a good place to start understanding the commutative laws and having especially an appreciation for the commutative law of multiplication. Along the way here, we've kind of introduced some fun little objects called polyominoes. I think they appeared a little bit interesting. We had those kind of zigzaggy ones like the Z or the T and the L. Next time we're going to play around a little bit more with them. Since we're good at counting now, we have our Hindu-Arabic number system, so we can count even big things. Let's have some fun with polyominoes next time. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.